But let's try to know what is meant by solenoid. Solenoid is nothing but it is large a large number of circular turns, okay, insulated large number of circular turns wound in the form of cylinder is known as what? Solenoid. Got it? A large number of circular turn wound in the form of cylinder is known as solenoid. So this is the actual solenoid. If it is little bit stressed, then it will be seen in this manner, but it should be wound very close to one another. Okay, now let's see the other pictures for this solenoid. Now if you cut this solenoid and if you see the cross section, okay, if you cut these cross sections here and if you see it, then top view, okay, you can see, or side view, if you cut it parallel to the plane of this paper, then you will see like this. These are the turns, okay, different turns of the solenoid. So likewise these are also the different turns of the solenoid. Don't think that this is of two conductors, okay, this is a one conductor here, okay, one conductor, another conductor, another conductor, like this. It keeps on continuously moving like this, okay, in that manner. So you have to take it this as a conductor. I am drawing in a very magnified way. You can think of like that. So what happened, the magnetic, when current is passing through these two ends of the solenoid, then what happened, current will be passing through it, and due to that current, magnetic field will be developed around this current carrying conductor. For this conductor also similar to all those like that, okay. So the total magnetic field of this solenoid will be along its axis. Got it? So what happened, if you take that the concentric circle as we have done in the case of infinitely long current carrying conductor, likewise here also the concentric circles are all over this current carrying conductor, okay. So what happened, for this conductor also, there will be a concentric circle of magnetic line of force like this. Now what happened, magnetic line of force will exist there, no doubt, but the magnetic field will exist inside the solenoid, that means along the axis of the solenoid, okay, not outside. Outside will be there, but near to this solenoid there will not be no magnetic field. Got it? In the case of an ideal solenoid. Why it is so? Because see, the magnetic line of force for this particular conductor is clockwise. Let's take it as clockwise. Here it is also clockwise. So what happens, somewhere here at this region the magnetic line of force is coming outward, but here in this case, for this magnetic line of force is getting inward. So one is coming outward, another is getting inward. So at this region somewhere here, the magnetic line of force cancel each other and neutralize the magnetic field that is produced by the one conductor with the another adjoining conductor, okay, similarly like that. So there will not be no magnetic field somewhere here, okay, outside the solenoid, I mean. Got it? So it is just like that. This will be used up when we try to express the magnetic field due to a solenoid. Let's try to see the actual solenoid, okay. The actual solenoid will be just like this, and it will be wound, okay, it will be wound very close to one another, okay, so that there will not be any leakage of what? Magnetic fields. Got it? In this way, right? Now if you see the cross section, the actual cross section like this, we may also have the picture in this way. This will be the actual picture that we are going to use it. Got it? If the direction of the current carrying conductor, okay, if the direction of the current carrying conductor is in this way, got it, then what happened, the magnetic field will be acting along this. If you take it that magnetic field is getting along this, that means this side will be acting as what? South pole, and this side will be acting as north pole. We have learned about that direction of the magnetic field, you know, of that circular coil. Suppose if you take it like this, if the current looking from this side, if it is what? Clockwise, then it will be of the shape S like this, right? The circular, suppose somewhere here, if you see the direction of the current seems to be the direction of the current is clockwise, then what happened, this side will be acting, this side will be acting as south pole, and the current will the magnetic field will be getting inward. So the magnetic field line of force will be getting inward, and if it is just opposite, if the magnetic line of force is coming outward, then watching from here, from this side, then the direction of the current will be anti-clockwise. Okay, in that way. So the direction of the magnetic field will exist only along the what axial line or inside the solenoid. Okay, inside the solenoid in the direction of the arrowhead given here. Okay, so what happened, this circular coil, if you take it that this is clockwise in direction, then what happened, current will be coming out from here and current will be getting in. So getting out the current, if the current is getting outward, then that is drawn by a dot. Okay, like this. So this represents what, outward. Okay, suppose if you puncture this with an arrowhead, then you will see just as a circular dot. Okay, why? Because the arrow is pointed, no? So you will see that as a pointed what, when the arrow is coming out. So just like that, when the current is coming out from the conductor, that will represent by a dot like this. And if the current is coming out from here and if it is getting in like this, the current is getting in, that means that getting in, okay, perpendicular to the plane of the paper, that is denoted by a cross mark like this, or X mark. So this may be you can have the mnemonic like this. The dot represents what, the circular portion of the arrow. This cross represents the cross mark of that feeder at the back of the arrow. You can take it in that way. So this is coming outward. Okay, dot represents coming outward, and this cross represents what, getting in. So the direction of the current is in this direction. From here it is coming out, got it, and it is getting in. So this X mark here represents what, the current getting inside, perpendicular to the plane of the paper and directed inward. Dot represents perpendicular to the plane and getting outward. Got it? So in that way. So why I am telling all these things, because it will be used up in the derivation of the magnetic field due to this solenoid. Okay, let's see. Now the same diagram that I have told you. So let's take it that B, capital B, be the magnetic field produced by the solenoid of having small n turns per unit length. So by applying that Ampere circuital law, let's try to see the line integral of B dot dl over this rectangular loop PQRS will be equal to what, mu naught times total current through the rectangular loop PQRS. Okay, now as I said, if we are going to take the line integral over this rectangular loop, then let's separate it into 4 parts. Okay, line integral from P to Q, second Q to R, third R to S, and fourth S to P, like that. Okay, and we know that those different parts, this, if the dl and magnetic field, if they are perpendicular, then it will give you 0 for this line integral. Got it? And if it is no magnetic field between S and R, then if it is 0, then this will be also 0. So your magnetic line integral of the magnetic field, what happened, from P to Q will only exist, but from what, Q to R, as your dl and magnetic field are perpendicular, cosine of 90 degree will come, so this will be 0. Okay, as magnetic field is 0, what happened, this will also give you 0. There is no contribution of the line integral of magnetic field. For this one also, as B and dl are perpendicular to each other, so this will give you 0. Okay, so only what remains is what, line integral of B dot dl from where to where, from P to Q of the rectangular loop. Okay, so that is what it is seen here. So your B is constant or uniform inside the solenoid, so you can take that B outside, and if you take it the integral of those small dl over this P to Q, then you will get it the whole length of this side of the rectangular loop PQ. That is nothing but it is equal to L. So mu naught times what? The total current, okay, the total turns in PQ. We need to find out that much amount of current will be flowing through this what? PQ of those turns on lying onto this PQ. So it will be equal to what? Mu naught times the total number of turns here, and if I is the current flowing through that one turn, how many turns are there? If there are n turns, then it will be n times that L. Okay, n means capital N. So L, capital N, will represent the total number of turns, and that total number of turns you can express it as n into L. Got it? So like that, NLI. So what happened if you cancel this L with this L on this side, then you will get magnetic field B will be equal to mu naught times Ni. Okay, thus the magnetic field induction at a point in the solenoid is independent of the length of the what? Amperian loop or rectangular loop, but depends upon on what? On to the number of turns per unit length of the solenoid. Okay, if the number of turns per unit length of the solenoid is large, then what happen? Magnetic field due to that solenoid will be also large. Of course, if a larger current is passed through that solenoid, more the magnetic field is there. Got it? So this is all about that of the magnetic field due to a solenoid. Okay, let's stop it here for today. Thank you.